Welcome back to Basic Biostatistics 2 and to model number 5. Model number 5 is about ANOVA tests. In this model, I will show you how to run a one-way ANOVA test and the corresponding non-parametric test, which is the Kruskal-Wallis test, and I'm going to show you how to make univariate ANOVA, which is a model where you try to compare a mean of a variable among three groups, considering a second variable in the independent variable window. Let's have a look at one example, and this will be in this exercise that we'd like to compare if there is a difference in the mean cholesterol value between the three different groups of physical activity. As you remember that if you have two groups, we can use a t-test to compare mean. If we have more than two groups, we have to use an ANOVA analysis. We find ANOVA under analysis, compare means, and as you remember from the last model, we have here the t-test, and the last one is a one-way ANOVA test. The null hypothesis is there's no difference in cholesterol level among the three different groups of physical activity. So let us choose the cholesterol level as a dependent variable, which is the continuous variable. Logically, you have to know that cholesterol level is normally distributed, because if it's not normally distributed, we have to use a non-parametric test. The factor will be the physical activity category, so we click the physical activity category and move into the factor. Now we've defined the model. As it's defined now, we're going to compare the cholesterol level among the three different physical activity categories. Before continue, we click on post hoc tests, because post hoc tests give us pairwise comparisons. It will compare us if there's a statistically significant difference in cholesterol level among the low physical activity and moderate physical activity group, or the low and the high physical activity group, or the moderate and the high physical activity group. After equivalence assumed of the post hoc tests, we can choose LSD or Bonferroni-Tukey. Each test has its advantages and disadvantages, which you probably have to read again from the theory classes you had previously. We click on continue. We go in options. In options, we select descriptive, homogeneity variance tests, and that's it. And continue. One-way ANOVA has assumption that the continuous variable has to be normally distributed and that the variance has to be equal, which means homogeneous, and that's why we have to run a homogeneity test of variances. If the variances are not equal, we cannot use a one-way ANOVA test, we have to use a non-parametric test. We click on OK, and we receive the test results. As you see, we receive several tables. The first table is descriptive analysis. It tells us the mean value of cholesterol for the low physical activity group, the moderate physical activity group, and the high physical activity group. We can already see there seems to be a tendency. There seems to be that the high physical activity group has a lower mean cholesterol values than the low physical activity group. However, from a descriptive statistics, we cannot know if this difference is statistically significant. We have other information like the standard deviation, standard error, the confidence interval, minimum, maximum. The second table we receive is the test of homogeneity variances. The null hypothesis is that there's no difference in the variances, which means the variances are equal. The leading statistic of the test is 1.851 with a p-value of 0.166. This is more than 0.05. This means we accept the null hypothesis and state there's no difference in the variances among the three groups. This is important because now we know that we fulfill all the assumptions of the one-way ANOVA test, and we can continue. If this test result results you statistically significant, you don't have to continue interpreting the table, but you have to run a non-parametric test. We go down to the third table, which is the result of the ANOVA test. The ANOVA test compares the between group sum of squares with the within groups of sum of squares. and he calculates an F value of the ANOVA test, which is 47.357. According to the F value, it calculates a p-value. The p-value in the one-way ANOVA is, in this example, 0.000, which is less than 0.05. This means that there's a statistically significant difference in the cholesterol value among the three different groups of physical activity. However, we don't know which groups differ from each other, because it might be that the group between low and high physical activity is statistically significant, or the group of moderate and high, low and moderate, or all the three groups differ statistically significantly from each other. Therefore, we ask for post hoc tests which answers these questions. Here we can see like the three different comparisons. You see in the first row, low physical activity compared to moderate physical activity has a mean difference of 0.85856, the standard error of the difference, and the p-value for the difference, which is statistically significant. Thus we know there is a statistically significant difference between low physical activity and moderate physical activity in respect to cholesterol. The second comparison is low physical activity with high physical activity, a mean difference of 1.835, p-value of 0.000, means also the low physical activity and the high physical activity group differ statistically significantly in respect to cholesterol. And what is missing basically is the moderate physical activity with high physical activity group. The same, we have a difference of 0.977, which is statistically significant. So we know in this case that all three groups differ statistically significantly from each other. So the cholesterol level is very different in the low physical activity group and the high physical activity group. What do we do if our continuous variable is not normally distributed, or if the variance is not homogeneous? For instance, we'd like to compare whether there's a statistically significant difference between the systolic blood pressure of month 1 among the three physical activity groups. We know that systolic blood pressure of month 1 is not normally distributed, so we have to use a non-parametric test, which is the Kruskal-Wallis test. Let me show you how we have to run the analysis. First, close the output file. We go to Analyze. In Analyze, we have, as you know already, the non-parametric tests, and in that case, we go to Independent Sample Tests. We click on Independent Sample Tests. It opens the window we already know, and here you see descriptions. You can find the Kruskal-Wallis test, one-way ANOVA for more than two groups, which means K samples. We leave the objective, automatically compare distributions across groups. We click on Fields. Here we select the systolic blood pressure of month 1, the variable we're interested in, and H, the physical activity categories as grouping variables, which consist of three groups. Before running the test, we have to choose the Kruskal-Wallis test. You already know that we have to go to Customize Tests. We have to click on Kruskal-Wallis test and select the Kruskal-Wallis test. The null hypothesis is there's no statistical significance difference in systolic blood pressure of month 1 in these three physical activity groups. We run the analysis, we receive a window, a table already know, with a null hypothesis stated, which is, as we just mentioned, that distribution of systolic blood pressure in month 1 is the same across categories of physical activity. The test we selected is a Kruskal-Wallis test with a p-value of 0.009. This is less than 0.05, and therefore we reject the null hypothesis and state there's a statistically significant difference in systolic blood pressure of month 1 among the three groups of physical activity. The thing is, we don't know which groups differ from each other. And this is the Kruskal-Wallis test will not give you an answer to that question. What you can do, you can use and explore, you can compare the medians between the groups to get a feeling or more or less idea which groups differ from each other. Or you can run non-parametric tests for two samples and using a Mann-Whitney test comparing group 1 with group 2, comparing group 2 with group 3, or comparing group 1 with group 3 if you're interested in finding out which group statistics significantly. The last one test I'd like to show you in ANOVA is univariate ANOVA, because as you remember we compared the cholesterol levels among the physical activity groups. But maybe we have also a difference in cholesterol among the smoking categories, the non-smoking and the smokers, and maybe there could be an interaction between physical activity and smoking. To put all this in the same model, we have to use univariate ANOVA. We go to Analyze, General Linear Models, and we find univariate. Univariate means a multivariate ANOVA or univariate ANOVA. We click on univariate and we receive a window which consists of a lot of white spots which we have to fill in. In multivariate ANOVA we have more than one null hypothesis. In this case we like to have cholesterol as a continuous variables. We like to have as a categorical variable in the same model smoking and physical activity category. The first null hypothesis is that there's no statistically significant difference in the cholesterol level among the three groups or categories of physical activity. The second null hypothesis is there's no statistically significant difference in the cholesterol level among the smokers and the non-smokers. And the third null hypothesis is there's no interaction of smoking and physical activity. This means the effect of physical activity on cholesterol is the same for smokers and non-smokers. How we build the model? We first of all select the continuous variable as dependent variable. And the dependent variable has to be continuous, has to be normally distributed, and we have to fulfill the assumptions of the homogeneity variance. The categorical variables, as in this case smoking status, we add fixed factors, as well as physical activity category, we add two fixed factors. In case you like to adjust the result for age of a continuous variable, you would add it to covariates. In our case, we are not interested in covariates, we're just interested in the fixed factors, in the categorical variables. If you click a model, the program has already selected the full factorial models, so we click on continue. We can have a look at contrast. In contrast, we can change reference categories we actually don't need, so we still click on continue. Under plots, we can ask the program to calculate, to show us a graph of lines. For instance, we choose the physical activity category as a horizontal axis. We like to have separate lines of the effect on cholesterol of the physical activity categories for the smokers, so we click smoking and move it into separate lines. Then we click on add, and this will construct us a nice picture. You can always play around with the program and try to change, for instance, add physical activity categories horizontal axis or separate lines for physical activity and smoking horizontal axis, and to see what kind of graphs the program will produce. Click on continue. Now we're interested in post hoc tests. Basically, we only need post hoc tests if the categorical variable has more than two groups, because if there are only two groups, if there's a difference, we know that the two groups differ. In this case, we have one variable, which is physical activity category, which has more than two categories. Are we interested in multiple comparisons? That's why we click on physical activity categories, we move it into post hoc tests for physical activity category. We choose LSD or Tukey, whatever you like to. And we click on continue. Now before running the test, we click on options. In options, we'd like to have the means. We can different the mean for cholesterol for the smoking categories. And for the physical activity categories, we move it into the display means window. We enter logical homogeneity test if we fulfill the assumptions, and descriptive statistics. If you're interested in other factors, you can select them based on the necessity of or your needs. You click on continues, and now you're ready to run the analysis. Clicking OK, it gives us several tables. It first of all gives us a table between subject factors, tells us that the continuous or categorical variable smoking status has two levels, has non-smokers and smokers, 30 observation each of the groups. The physical activity category has three categories, low, moderate and high physical activity, with the corresponding numbers of observation each category. The second window, or the second table, gives us the descriptive statistics. It gives us the mean values among the non-smoking bars for the low physical activity, non-smokers, and the moderate physical activity, and bars with high physical activity who are not smoking. It gives us the same for the smoking bars, so low statistics, the mean value, the standard deviation, and the number of observations we have in each group. The third table gives us a test of the Levens test for equality of variances, so that the variances are the same. We know that the null hypothesis is that there's no statistically significant difference in the variance between the groups. The F value is test value, and sig is the p-value of the test for homogeneity variances. This is more than 0.05. This means we accept the null hypothesis, and we state that there's no statistical significant difference in the variances of the different groups. And this also means that we fulfill with the assumptions, and we can continue analyzing the data and interpreting the results. Then we have in the fourth table the results of the Univert ANOVA tests. Three rows which are important. The row for smoking, the row for the variable physical activity category, and the interaction terms. Because these three rows answer our three null hypotheses. The first null hypothesis was, is there a statistically significant difference in cholesterol levels among the smokers and non-smokers? We have here the test statistics, and F value 0.078, a p-value of 0.782, which is more than 0.05. This means we accept the null hypothesis. There's no statistically significant difference in cholesterol among smokers and non-smokers. The second row answers the null hypothesis, is there statistically significant difference in cholesterol levels among the physical activity categories? The p-value is less than 0.005, which means we reject the null hypothesis, and we conclude, yes, there is a statistically significant difference in cholesterol among the three groups. And the third null hypothesis is there an interaction between smoking and physical activity, or does smoking affect the effect of physical activity in cholesterol? We have a p-value of 0.526, and this means that no. We accept the null hypothesis, there's no interaction between smoking and physical activity category. In comparison or compared to the model, we had only physical activity category. This model includes smoking, and this model adjusts the result for the factor of smoking, as it's superior than the previous model. The fifth table is a summary table. We ask for descriptives. It tells us the mean value of cholesterol for non-smoking barbs and smoking barbs. And the same for the physical activity categories, where we see actually mean value decreases from low physical activity until high physical activity from 6.671 to 4.822. It also gives you the 95% confidence interval, the lower and the upper bound. We have more. We have the multiple comparison table for the physical activity. We have the comparison between low physical activity and moderate physical activity, statistically significant. We have the comparison from low physical activity with high physical activity, statistically significant, and the comparison of moderate and high physical activity, also statistically significant. So all three groups differ from each other. And the last result we have is the profile plot we asked for. We have on the y-axis the estimated means of cholesterol. We get the cholesterol values. On the x-axis we have the physical activity categories as asked. On the horizontal axis we have the low physical activity, the moderate physical activity, the high physical activity, and separate lines for smokers and non-smokers. We see the tendency is the same among the smokers and non-smokers. The higher physical activity, the lower the cholesterol level. We also know that if the lines are parallel, more or less parallel, that there's no interaction. If the lines would cross and be different, one line for instance increasing, the other line decreasing, this would mean that we have interaction. In a graphical way, logically we have to consider the p-value of the interaction term of the two variables. This is all I want to teach you in regard to ANOVA analysis in this basic biostatistics 2 course. If you're interested in more sophisticated analysis of general linear model, I will refer to a further course in future, which will be Basic Biostatistics 3. However, with what I was teaching you today, you will be able to analyze the majority of the data of your thesis or your PhD work. Thank you very much. I invite you now to the quiz once you're familiar with how to run the analysis and the exercises. And see you soon in module number 6.